Okay. I'm going to run through a quick mesh analysis procedure for this circuit. The procedures that we follow for mesh analysis come under a few small processes that we need to consider. Right, first thing being we need to consider mesh analysis using Kirchhoff's laws, namely Kirchhoff's voltage law and Kirchhoff's current law. We're going to apply both of these laws to our circuit. So one of the first things that I like to discuss is making sure that people consider drawing their circuit nice and big. Making sure that it is in a format that they can annotate, and I'll show you the kind of steps to doing that. So I'll just quickly select a better pen, digger, different colour perhaps, maybe a slightly bolder colour. And we'll use a kind of bright pink, which, well, perhaps not, it's a little bit on the red side, I think. Something edging towards maybe an orange colour, perhaps. There we are. So, draw your circuit nice and big on your page. Helps you to annotate the drawing, the circuit well enough. Label your network loops on the diagram. So what I'm going to do is I'm going to consider two loops. Now we know from the polarity of this cell here that the conventional current is going to flow out in this direction, and the same with this one. So two cells pointing in the same direction, the currents meeting. If we were to consider the loops then, I typically just start from the left hand side, moving my way around in a clockwise direction. So I would typically consider this as being loop 1, and this one being loop 2, following the current around the circuit in the conventional sense, so not electron current. So I'm going to label my currents then. I'm going to call this one here current I1 and this one here current I2. So I'm considering applying Kirchhoff's law obviously at this point, which means that because of the polarities of the batteries, in other words the currents are going towards each other, I'm going to call this current here I1 plus I2. So let's take a look at what we've done. We've drawn our circuit nice and big, we've labelled our loops, we have assumed the battery's discharge current and entered them onto the diagram, and we have applied Kirchhoff's current law. Now what we're going to do is select the two loops, and we're going to build an equation for Kirchhoff's voltage law. So let's consider this over here. We know from Kirchhoff's voltage law that, I'm going to paraphrase it, the supply voltage is going to be equal to the sum of the voltage drops around the circuit, etc., etc. So I'm going to simply apply that, but subbing in Ohm's law for V. In other words, I times R. So looking at loop 1, we have 20 is equal to 8 ohms. That 8 ohms came from there. Now we are thinking about the voltage drop across the 8 ohm resistor, therefore it's going to be 8 times I1. So this would be the V 8 ohm resistor, if you want to think of it that way. We get that from the fact that the V8 ohm would come from I times R. So I've rewritten it as 8 times I, so I've just reversed the R round about the other way. And then from there I'm going to add up the currents flowing down through the branch C to F. So the branch from C to F is going to be from here down to here in this direction. So that's going to be 14 I1 plus I2. Then all I need to do is simply take my brackets here and remove them. So I'll rewrite out that line. So 8 plus 14 is going to be 22 I1 plus 14 I2. So all I've done here is I've multiplied out each term inside the brackets by 14, and then I've gathered my like terms, 14I1 plus 8I1. And I'm going to go ahead and call that equation 1. Let's do loop 2. Loop 2 is going to be the same process. We've got 30 volts, and then we're talking about the current I2 moving around loop 2. So we have 30 is equal to 6I2 plus, and then it's a repetition of that first line, the branch C through F, I1 plus I2. Multiplying out the brackets and then gathering my like terms, I get 30 is equal to 14I1 plus 20I2. So all I've done there is I've multiplied out the brackets again, and I've taken 14I2 and 6I2 and I've added them together. So 14 and 6I2, added them together to get 20. And then to keep everything nice and neat and in order, I've put my I1 term to the left. I've just automatically moved that over. You could add that as an extra step if you want to. So I'm going to go ahead and call that equation 2. So now what I've done is I've built 2 loop equations. And those 2 loop equations will allow me to solve for one of the currents. So as a matter of course, what I tend to do is just rewrite out the loop equations that I've completed. So equation 1, 20 equals 22I1 plus 14I2. That's equation 1. And right underneath it, 30 equals 14I1 plus 20I2. Always double checking my work in case I make some silly mistake. So that's all looking good. I've got my voltages from the supply, 20 volts and 30 volts. And then I've got 2 sets of currents, I1 and I2, on top of each other. What we now have is 2 simultaneous equations, which means that we can eliminate one of the unknown values. So if you might remember from simultaneous equations, you can have 2 unknowns, I1 and I2. If we remove one of these, then we can figure out our unknown current with only a single unknown term. At this stage you should know this, and we'll go ahead and work this out. So equation 2 and equation 1 have been written out. What I'm going to do is I'm just going to quickly move these over a wee bit, I think, just to give myself a little bit more room, because we're now kind of moving away from the schematic ever so slightly. So what I'd like to do here is consider how I can eliminate one of my terms. In this case, I've got two sets of even numbers across I1 and I2, being 22 and 14 and 14 and 20. So it doesn't really matter which one I remove, but I tend to just look for the even numbers and remove them. And what I tend to do is just consider with something that is a little bit harder with different numbers, I tend to consider just taking this number and multiplying it by 14 and this number and multiplying it by 22. So if I write out my expression here rather, so take equation 1 and multiply it by 14, and take equation 2 and multiply it by 22. So I'm multiplying each term, this one, and this one, by 14. And then I'm going to do the same on the bottom. I'm going to multiply 20, 14, and 30 by 22. So let's go ahead and do that. So 14 times 20 is 280. Times 22 is 308. Not forgetting to write in my terms. And then times 14 is 196. So that's me completed the operation of multiplying each term, or each set of digits, numbers, by 14. I'm going to carry out the same process through equation 2. That is, multiply everything by 22 along the line equation 2. So we'll end up with 30 times 22 is 660. 22 times 14 is 308. I'm expecting that to happen because what I've chosen to do is eliminate I1. And then 22 times 20 is 440. So now that I have made my two terms in equation 1 and equation 2, my two terms that are describing I1, or rather the voltage across that particular branch, because I've now got them matching, I can now subtract them, I can eliminate them. So in other words, effectively cancelling them out. So, if we're going to eliminate this one here, that 308 take away 308 gives me 0. So let's go to the rest of our equation. This is obviously going to work out. So let's go to the rest of our equation then. 280 minus 660, so I'm subtracting. That's going to leave me with minus 380. As I said, 308 minus 308 gives me 0, and then 196 minus 440 gives me minus 244. And again, not forgetting to write in my unknown term I2. So we now have an equation that has negative 380 on one side and negative 244 on the other, and now only one unknown term, which means we can rearrange this to solve for I2. So I'll take that as a step underneath. Minus 380 over minus 244. And that's going to give me 1.56 amps. Therefore, I2 equals 1.56 amps. Now that we've actually figured out one of our currents, I2, well, we still need to figure out I1. So it's entirely up to you how you do this, but we can substitute I2 anywhere where we see the term I2, so I2 equal to 1.56, and we can figure that out, bringing our equation, any one of our equations, down to, again, only one variable term. So let's go ahead and write that out. And just as a force of habit, I tend to pick the easier equation. In this case, they're both quite easy because they're all round numbers and there's no negatives or anything. So I'm just going to rewrite out my equation 1. 20 equals 22I1 plus 14 times 1.56. So I've literally substituted this thing here into that equation I1. Equation 1 for I2. So 14 times 1.56 is 21.8. And then we're left with 22I1 and 20 is our supply. Rearranging our equation, 20 take 21.8 is equal to 22I1. And I'm just going to go ahead and divide both sides by 22, effectively eliminating this here. I'll rub that out. So this gives us I1 being equal to negative 0.082 amps. So we've now calculated both our currents I1 and I2. One thing we haven't done is we haven't figured out a third current. Let's go back to our mesh analysis. This 20 volt cell is producing I1, which is flowing around the branch from B, C, F, A and back to the battery. So the current flowing through the 8 ohm resistor is I1. Likewise, the 30 volt cell has this loop here going from D, C, F to E. So the current flowing through the 6 ohm resistor is I2, but the 14 ohm resistor is the sum of I1 plus I2. So therefore, the final current that we need to work out is I1 plus I2. Which is going to be 1.56. I realise that I've mixed these up, but it doesn't really matter. Plus negative 0.082. Now, it does depend on what you're going to be working out in your circuit. It depends on what your question is asking. In some cases, a question might ask you to calculate only the current flowing through the 6 ohm resistor. It might ask you to calculate the current flowing through the 8 ohm resistor. And likewise, it could also ask you, and in many cases it asks you to carry out a calculation for the current flowing through the 14 ohm resistor. So it depends on the current, it depends on the question and the current and concern that's being looked at. It's also going to depend on the size of the cell. So in this case, we can assume that if it was a current flowing through the 6 ohm resistor, then it's literally going to be I2. But if it was the current flowing through the 8 ohm resistor, then you're going to have a difference between I1 and I2. Okay, because the 30 volt cell is producing an EMF that is pushing against the current flow coming from the 20 volt cell. So that is mesh analysis, and one little thing you can do when you're carrying out these checks, when you're carrying out these calculations, is you can take both of your currents, I1 and I2, here and here, and you can substitute them back into either one of your loop equations, and you should get a pretty close approximation to the answer. So we've worked out our unknown terms I1 and I2. If we substitute them into our equation, we will find out our answer, which means that you can do a self-check in the exam or in any practice tests. You could make up your own numbers and just do your own practice, and if you get within a good approximation of this, any one of these answers, 20 or 30, depending on which equation you use, then you know you've done it right. And that is mesh analysis with Kirchhoff's laws using KVL and considering KCL as well.